So welcome back, and here we are going to discuss about the oligosaccharides and polysaccharides. The simplest of the oligosaccharides is a disaccharide, which is formed of two monosaccharide units, which are bounded by glycosidic bond, which we have already mentioned in the previous presentation. What is glycosidic linkage? I hope you remember that in glycosidic linkage, two monosaccharide units come together, wherein the hydroxyl group on the anomeric carbon of the first monosaccharide binds with hydroxyl group in the second monosaccharide. It could be any of the hydroxyl group. It needn't be on the first itself. It can be anyone. Okay, but the first one, it is hydroxyl group on the anomeric carbon is the one which get into the bonding. Okay, so hydroxyl group on the anomeric carbon of the first monosaccharide, it forms a glycosidic linkage with the hydroxyl group on the second. Fine. Here, what happens during the glycosidic bond? When we discussed about the reducing ability of a sugar, we were discussing on the reducing ability of an open chain form. I hope you remember, isn't it? And here you can see whenever the reducing property we were discussing, it was the here. Okay, so whether it is the open chain form or the what you call cyclized form, it is the first carbon which is actually reducing the cupric into cuprous. Okay, it is because of the first free carbon. Only when the first carbon is free, this it can show the reducing ability. Okay, it can undergo oxidation. Okay, this is the carbon which undergoes oxidation during the redox reaction. Okay, so here what happens, because of this one, it will reduce cupric into cuprous. Okay, at the same time it undergoes oxidation, right? When it gets cyclized, what happens? The C1 becomes anomeric carbon, isn't it? And if the anomeric carbon is free, obviously that particular sugar is reducing. Okay, so this applies to disaccharides as well. That is what we are discussing here. Okay, that applies to disaccharides as well. So in the disaccharides, what happens is the here the first carbon, since the anomeric carbon which was supposed to be free in a reducing sugar, it is the one which gets into the glycosidic bond. This because here there is no reducing ability. What about this one? Here in the case of maltose, the second glucose have a free anomeric carbon. The first carbon is free. So what happens? There is a free anomeric carbon in this particular disaccharide. So it can show the reducing ability. It can take up a reduction of the cupric to cuprous. Okay, so this is what here I would like to tell. Okay. Now, when you describe glycosidic bond is a covalent bond formed by the as a condensation product between the hydroxyl on the anomeric carbon of the first sugar with the hydroxyl on the second sugar. Okay. When we are speaking about the disaccharides, it is always the hydroxyl on the second sugar. When you are asked to write what is a glycosidic bond, it needn't be always a second sugar. It can be any compound which contains alcohol, and it is ready to react with the hydroxyl on the anomeric carbon of the first monosaccharide. Okay, so the product formed, it is known as a glycoside. Okay, and how do you name that? Okay, how do you name a particular disaccharide? The first, these are few points which you can follow to name the disaccharide. First one is like we have to name the bond with the configuration, okay, of the first monosaccharide unit. So obviously disaccharide, it is formed of two monosaccharide units, but we will be considering, while naming, we will be considering only the configuration of the first monosaccharide, whether it is alpha or beta form. Okay, then next what we do is we insert furano or pyrano to the 6-membered or 5-membered structure. Okay, so if it is gluco, it will be glucopyranose. If it is fructo, it will be fructofuranose. Okay. Likewise, we will be modifying the name of the residues. Fine. Now, indicate the parenthesis, that is in brackets. We will write the number, the 2 carbon atoms joined by the glycosidic bond, and with an arrow connecting the 2 numbers. Okay. So which carbons are going into the bonding? Okay, obviously the first sugar, it will be in the case of pyranose, in glucose, galactose, etc., it will be the first anomeric carbon which gets into the glycosidic bond formation. While if it is the fructofuranose, obviously it will be the second one, right? So it will be one arrow and then the number of carbon which makes up. Here you can see with this example, right? First, we have to write the name. If it is so, this is alpha 1,4 bond. Okay, so the first monosaccharide unit is alpha form, so that comes first, and then what we do, we modify the names, isn't it, of the reducing of the residues with furano or pyrano. So it is glucopyranoside and glucopyranose. We have modified it, and then what it is, we have to put it in brackets. The numbers, the number of actually the carbon number of the reducing of the residues which comes into glycosidic bond linkage, isn't it? So here C1 with C4, and that is represented as 1 arrow 4. Okay, so then what we have to follow, name the second residue. Okay, after once the bracket is closed, we have to write the second name of the second residue. Now, so that is a disaccharide. If it is a trisaccharide, the same is followed, but we will add one more. That is it. Okay, so we can go here. We will be discussing on the three most abundant disaccharides, that is maltose, lactose, and sucrose. Okay, the structure, the where it is present, and the functions. Okay, maltose, it is otherwise the malt sugar. It is actually hydrolysis product of starch and glycogen, and maltose, it is composed of two glucose units, and so once the maltose is hydrolyzed, obviously it produces two glucose molecules. Okay, it is linked by alpha 1,4 glycosidic linkage. That means the first monosaccharide glucose, first glucose is alpha form. The second glucose, whether it is alpha or beta, it doesn't matter, because it is this first monosaccharide, it is forming a bond with the fourth carbon, right? So whether this one is alpha or beta position, it doesn't matter. Fine. Now coming back here, the first sugar, it is alpha D glucose, and how do we name? Alpha D glucopyranoside, right? And it is the first carbon, it forms a glycosidic bond with the fourth carbon, and then with the fourth carbon of the second D glucose. Okay, so it is actually 1,4 linkage. Okay, here you can see since both hydroxyl groups of the D glucose were below the plane, here if you take the what you call this monosaccharide unit residue alone, it could have been H and OH here, right? So what happens here? So OH is below the plane, and over here what happens? In this residue, before the bonding is formed, again the fourth carbon will be having OH below the plane. So what happens to the bond once it is formed? The bond will be below the plane. Okay, so that is what is represented here. Okay, now here you can see when you speak about the anomeric carbon, this anomeric carbon of the first glucose, it is getting into glycosidic bond linkage. What happens to the second, the anomeric carbon on the second glucose? It is free. So what happens? It can act as a reducing sugar. Okay, so maltose comes from hydrolysis of large polymeric oligosaccharides such as starch and glycogen, and is in turn hydrolyzed into glucose by the enzyme maltase. Okay, because the disaccharide retains a free anomeric carbon on the second monosaccharide, maltose is a reducing sugar. Fine. Now next one is lactose, and it is the disaccharide which actually gives a sweetness to the milk. Okay, it is a disaccharide of milk, and it consists of two beta D glucose and alpha D glucose bonded between them through beta 1,4 glycosidic linkage. So here we have beta 1,4 glycosidic linkage. Fine, and it is beta D glucose and then alpha D glucose. Okay, so you can see here, what is a beta then? Why the name beta? Because a hydroxyl is above the plane. Hydroxyl on the anomeric carbon is above the plane. Okay, so here it is a hydroxyl group, and in the case of alpha D glucose, how it has to be? Fourth carbon is having hydroxyl below the plane. So the bond is formed in this way, isn't it? So it is slightly twisted, right? It is across the plane. Fine. So you have the lactose with beta 1,4 glycosidic bond. Okay. Lactose, it is hydrolyzed to beta D glucose and alpha D glucose, beta D galactose and alpha D glucose, once hydrolyzed by the enzyme lactase. In case of human beings, it is the lactase which acts on lactose for breaking for the hydrolysis into galactose and glucose. Okay. Now next is sucrose. Okay. Coming back here, here also you can see this was the anomeric carbon, right? The C1. Okay. If this is a C4, obviously this is a C1 over here. So in the case of galactose, obviously the anomeric carbon is get into the glycosidic linkage. What about the alpha D glucose, the second monosaccharide? The anomeric carbon is free. So here it is a reducing sugar because there is a free anomeric carbon which can actually get reduce the cupric into cuprous. Okay, here regarding the sucrose. Okay, sucrose, it is the common table sugar. It is obtained commercially from sugar cane or sugar beets, and here it is actually a disaccharide of alpha D glucose with beta D fructose. Okay, beta D fructose through alpha 1,2 glycosidic bond. Okay, so the anomeric carbon of the alpha D glucose, the hydroxyl group on the anomeric carbon of the alpha D glucose makes a glycosidic bond with the hydroxyl group on the second carbon, which is an anomeric carbon, okay, of the fructofuranose. I hope it is clear. In the fructose, what happens? Fructose, it is a 5-membered ring. It is a furanose structure, right? And unlike the pyronosyl structure, where you can see in glucose how it is in pyronosyl structure, in pyranose form, this first carbon is the anomeric carbon. But in furanose form, the second carbon is the, yeah, it is the anomeric carbon. Okay, here what has happened? Both the monosaccharides had the what you call anomeric carbon going into the glycosidic bond. So in both the cases, the anomeric carbon is already engaged in glycosidic bond, so it is not free, and hence what happens? It is not a reducing sugar. So sucrose will not give a positive result in a Fielding's test. Okay, so the anomeric carbon atom of glucose unit and a fructose unit are joined in this disaccharide. Okay, so this configuration is alpha for glucose and beta for fructose. So alpha D glucose and beta D fructose, through the two anomeric carbons, it forms a glycosidic bond. And sucrose, it can be cleaved by the enzyme sucrase into the respective monosaccharide units. Okay, so regarding this, when we compare sucrose with maltose and lactose, sucrose contains no free anomeric carbon atom, and hence the anomeric carbons of both monosaccharide units are involved in the glycosidic bond. And so what happens? It is never a reducing sugar. Okay, it is a non-reducing sugar, and it is almost stable with respect to oxidation. Okay, so because of its stability during towards the oxidation process, it is a suitable molecule for the storage and transport of energy in plants. Okay, so that is with regard to the disaccharides. Okay, so these are the different disaccharides. You can see here sucrose, it is alpha D glucose and beta D fructose which comes into play, which comes together to form the disaccharide, and through the bonding alpha 1,2 glycosidic bond. Okay, and where is it found? It is found in sugar cane, sugar beets, and sorghum, and some fruits and vegetables. Okay, then what about lactose? Lactose, it is alpha D galactose and beta D glucose through the bond alpha 1,4. Okay, and then it is found in the milk, right? Maltose, it is alpha 1,4 bonding between alpha D glucose and alpha D glucose. Okay, and it is formed by enzymatic hydrolysis of starch. Okay, it is found in germinating cereals and malt. Right, there is isomaltose. It is alpha 1,6. Instead of 4, it will be 6. So I hope you remember when you, yeah, here. So which is the 6th carbon? This is the 4th carbon, isn't it? The 5th and 6th. So the hydroxyl over here, it forms a bond with the what you call the C1 carbon. Okay, so it is between them, this. Okay, so that is a isomaltose. Okay, 1,6 alpha glucose and alpha glucose through alpha 1,6 bonding. Okay, and trehalose, it is yet another disaccharide which is found in the insect hemolymph, and also in yeast and fungi, and there it is formed by alpha glucose and alpha glucose through 1-to-1 bonding. Okay, so trehalose is a non-reducing sugar. Why? Because both the anomeric carbon, it is forming the what you call the glucosidic bond. Okay, fine. Thank you.